everybody for being here today. This is going to be interesting because this is the first one of these I've done as a Zoom presenter. So we'll see how it all goes. What I'm going to present today is kind of a summary of an experiment that was completed during the summer of 2019. It's some things we did on the farm I work for, and hopefully you guys get as much out of it as I did. That's my goal. I'm going to change his housekeeping just a little tiny bit, and that is I'm going to present a section, and there's places where I'll pause and I'll try to glance over and see if there are in fact questions that have been asked, and if there are questions that have been asked, I'll try to answer them at that point in time. And then also I'm hoping to get finished in 35-ish minutes, so we have 10 or so minutes at the end if there are questions anybody has along the way. So without further ado, let's kind of jump right into this. First, I want to start with a little bit of a tech background and a few of the basics. And I will tell you that one of the biggest problems people have in communication is they don't agree on terms ahead of time. So we're gonna talk about, when I use words, what I mean by them, so that way as we go through the presentation, it will make a lot more sense to you. For those of you that are purists, yes, I will be taking just a little bit of liberty on some of these items. So, artificial intelligence. What is artificial intelligence? I like to define artificial intelligence as computers making decisions. What do I mean by that? And on the surface, that's an easy one to disagree with. I don't think artificial intelligence is about computers making decisions. It's about computers learning to do this or computers learning to do that. But at the end, that's kind of the goal of artificial intelligence, is to have computers help us make decisions. When it's boiled down to its basic parts, I think that it's important that we define it more or less that way. As a group, what I would challenge each of you to do as you go forward out of here, take a look at what you consider artificial intelligence is and see how it applies on some of this. Sometimes an example does a better job, if you will, of making this understandable. So some examples of artificial intelligence in our real lives. I believe everybody at this point in time knows how to say, hey Google, hey Siri, Alexa. We've all used that sort of thing, but it goes deeper than that. We have self-driving cars. People now have I drive my wife's car, and it drives me nuts because it beeps at me when I drift out of my lane. It beeps at me when I'm following too closely. It does all of these things that you would not expect. And we can't forget my best friend in the top right slide of all of this, and that's Wall-E. And Wall-E is kind of the really cool artificial intelligence guy that was in one of my favorite Disney movies. So what can we do with artificial intelligence? Or what is artificial intelligence? What can we do with it? If you take, I love this slide. I stole it. I didn't make it up. If you go out on the internet, you can find it. I think this is a fantastic slide that you can show and actually see where we're at with it. What can we actually do with artificial intelligence? Hang on a second. Is my slides not updating? Are you guys all seeing? And am I not getting the fifth slide, which is the big graphic on it?
No, you still have the initial one up.
Goodness, how did that happen? Well, that's not good. How are we going to do that? I'm going to do this just a little bit differently because for whatever reason, it didn't update my slide. Huh. See, I told you we'd have technical difficulties. Well, you know what I'm going to try to do here? Because I got to do this way. I'm going to just share this screen right here. We're going to do this a little bit differently. Okay, now are you seeing a slide with three concentric circles and one off to the side?
Yes.
Okay, we'll do it this way. It's not the way I wanted to do it, but we'll do it this way. So what can we do with artificial intelligence? Artificial intelligence is kind of the combination of AI, machine learning. If you take historical data and add it to AI, you come up with machine learning. If you take machine learning and add in training data, you can get deep learning. If you combine all three, you can get to what's called computer vision. And what if we can recombine the machine learning with the computer vision? And that's kind of the road we went down. And so one of the things to keep in mind is computers are great at spotting patterns that we don't actually see ourselves. So from there, and I'm just checking, did we jump to the next slide?
Yes, you did.
All right, now I won't check again. So I will say that it's everywhere. Red light cameras. Has anybody been in a city that has red light cameras and will stop you? How do they get your license number? How do they figure that out? That's a function of AI. Facial recognition. And you see it in the movies, you see it in a lot of places, but how would you describe a face versus how does a computer describe a face? If you look at the top left picture on this, where it's showing staff and contractor and visitor and some of those things, that's defining a face and defining characteristics. And as you delve into the world of AI and machine learning, you learn very quickly that computers define a lot of these things very, very differently than we would define these things. Cars. One of the things that is currently fascinating me is the self-driving cars or the lane assist. If you've driven a car now and you get over to the side of the road and you're going to drift off the road or you're going to drift across the center line and all of a sudden your steering wheel starts vibrating, it's just amazing to me how with the steering wheel vibrating, how it knows. And it knows if there's a line, it knows if there's a dotted line. It's better if there's a line, but it can sometimes just see the crack on the side of the road. How does it learn that and how does it know that? It can't be programmed for every possible condition. So it's learning about the roads you drive on and things like that as time goes by, and they all get better. Fascinating to me. But I didn't come to talk about that. I came to talk about agriculture. One of the big things that we all see, and we see them flying around, and half of the people out there own drones now. In the ag space, there's all kinds of drones. I call your attention to the center one where, on the left in the center, we have the RGB portion of it. On the right, we have the NDVI portion, which is the same exact picture almost right next to one another. But one of them is an infrared picture. One of them is a picture you can see with your eye. And what the NDVI does for us is it allows us to see different moisture contents and determine some plant health items. People are rushing very quickly to find ways to use these images and say, this is a healthy plant, this is a sick plant. And what they're finding is, in many ways, this can sometimes demonstrate problems that we don't see with our eye because the computer sees slight differences in the hues that we don't pick up. Then they see it at a level that we can't see on the images. So that makes it can learn along the way. This is bad, this is good, and then it'll identify it for us. But jumping in even deeper, everybody thinks of John Deere as the people that make the big green tractors, and the big green tractors are what everyone's excited about. John Deere's rebranded itself in the last few years. They call themselves a software company. It's really amazing to me that John Deere is a software company. What does that mean to all of us? Well, I'll call your attention on this particular slide to the top right photo. One of the things John Deere has done, in addition to the different precision ag things they've done and all the stuff that really is a big deal, they're now piloting a program where on the big ag sprayers, they will put a camera on the forward side of it, and that camera will process the image that the sprayer is about to go over, and in less than a second will decide if it's a weed or not, and if it's a weed, it'll spray it as it goes by it. This kind of targeted spraying allows them to eliminate broadcast spraying, drive down costs, and all kinds of wonderful, wonderful things that they like to say. But one of my quotes, my favorite quotes from John Deere is, machine learning and artificial intelligence in agriculture is hard. And on a lot of their literature, they'll show the bottom right picture where they have the corn and the soybeans sitting there talking about, well, this is a difficult thing to do with agriculture in general. Imagine trying to counter, identify, or find problems with seeds. And that to me is fascinating. But again, we made it to ag. I want to make for all of you a business case for potatoes. So I come from a potato farm, a potato agribusiness. Fun fact that a lot of you may or may not know, I don't know the answer to this, but a really fun fact is that Wisconsin is one of the top producing potato states in the United States. Nearly all of Wisconsin's potatoes are grown right here in the Central Sands region. Before I came here, I never would have guessed that potatoes are considered a high cost to grow crop, meaning it costs a lot of money to grow them, so you want to get it right. There's a ton of monitoring that must happen and a large volume of data that has to be collected. Compared to other crops, the number of experts in the field are minimal, and the ability to leverage the knowledge of those experts is difficult, meaning for corn farmers, there's experts everywhere. For potato farmers, there's not quite as many experts along the way. Whoops, I jumped way too far ahead there. So that gave us a challenge. The challenge we had, determine our field progress, project our yield, how are we doing? Project our size distribution. And then because of that, timely information will make for better decisions. On any given day, we want to know how the potatoes are doing. We want to know what our yield is, but more importantly, we want to know what our size distribution is. Meaning if we harvested these potatoes today, or if they stay on track, how many of the ones that would be perfect to put in the oven for baking would we get? How many of the really small ones would we get? How many of the larger ones would we get? And that helps us make better decisions for what we're going to do with the field down the road and how we're going to manage the field. That becomes important because one of the challenges I'll give to all of you, you're at a conference or if you're sitting at home, if you have a bag of potato chips, if you go to the local convenience store and pick up a small bag of potato chips and open it up, the small personal ones you buy for a couple bucks, and look inside of it, you'll notice that most of the chips aren't broken. They're nice and round and the right size to fit inside the bag. Then if you go to the grocery store and you buy the bigger bag of potato chips and open it up, you'll notice all of those potato chips are one whole slice of potato and they're not broken either. That's the goal of the potato chip manufacturers. They present better. Kind of a neat deal. For us to get our product to market, we need to make sure we have the right size potato that our customer wants. So if they're doing small bags, that's one thing. If they're doing large bags, that's another thing. If they're going into a grocery store, that's a third thing. If they're going into food service where they don't care about the size, they just want a lot of weight to make mashed potatoes, they can be really large. All of these things, the sooner we can determine it, the better off we are. So that's kind of the challenge we had to get to. The current process. If you look on the far right side, we go to the field, we walk through the field, we take pictures, we bag up some samples, we take those back to a machine called the Exeter that I'll show you a picture of here in a minute. And then after it runs through that machine, it will actually, we marry the data together with it for the reports for agronomic analysis. Here's the problem. We have all kinds of delays with that. There's inconsistencies in the sampling. When you have, we use high school interns in the summer to do our scouting all over the 5-county area. And they don't necessarily always pick up and gather up all the things they're supposed to pick up and gather up. So they may leave a couple behind. And then once they get the data back, they lose the tags. There's all kinds of problems inherent in the process that causes us problems along the way. So when we get it back, what do we do with them? So they bag up the potatoes, they've taken a picture of it, they bring it back to this machine here. This machine here, the potatoes come in, they go in that big blue box. Inside of that big blue box, they get their picture taken under a strobe light, and that will actually give us some pictures of what the potatoes look like. It'll actually calculate the size, the length, and the width, and you can't see it by the picture, but it actually is rolling the potato as it goes through, so it hopefully gets 3 dimensions of it. Very inefficient process. It's good, but it's not great. So our idea was we can do better than this. I'm going to take just one slide, just a little bit about us. We are a company that exists in a lot of different states. We're based here in Wisconsin. We farm here in Wisconsin. We have world-class agronomic talent. We have 2 of the top agronomists running all of our agronomy R&D and our agronomy on our farming operations. I believe the technology organization is awesome because that's what my organization, my background, I come from a product development background, so I'm used to working with scientists to commercialize their products. We also, for years, have performed varietal R&D. What does that mean? You know, you go to the store, the easiest way to explain it is you can see red potatoes and you can see white potatoes and you can see russet potatoes and yellows. Those are different varieties. And every one of those varieties has size characteristics and weight characteristics and things like that. We've collected that data. We've been an R&D farm for many, many, many years. We also work with growers in a number of states that do the same thing. So if you combine our agronomic talent with all the data we've collected with computers today, we kind of came up with what would be known as a crazy idea. So what I'm going to do, I haven't seen any questions asked. If anybody has a question before I jump into the crazy idea portion of this, this would be a great time to ask it. Otherwise, we can come back around to it at the end. Okay, so I'll move on real quickly from there. So the crazy idea is what if we took years and years and years worth of sizing, weight, distribution data, combined it with our agronomic insights, and then handed it to a computer and said, hey, computer, think for us. What could that computer accomplish for us? Where could we get with a project like that? So right now, we're taking pictures in the field anyway. That's pretty easy. What if we only slightly modified the photo process? That'd be kind of cool. What if we could size the potatoes directly from the photo? And then what if machine learning could leverage over 2 million historical samples, and then we could accurately predict the yield and distribution just from that photo? Would that be a win? And that was what I proposed to the agronomy team, and that's what I proposed to my team. Guys, can we do all this? And we decided to start this experiment based on all of that. So boy, what a journey. It was interesting, starting with the tools of the trade. Interestingly enough, I've got a primarily Microsoft shop at my office. I had a bunch of programmers that really were old SQL report type programmers, didn't think a lot of some of the newer technologies. And so how are we going to move this in a right direction? So the first thing we had to do was look at what tools are out there. And if you're interested at all in machine learning or AI or computer vision, I'll show you some of the work we did. We took a look at Windows and at Linux. I will tell you that Windows was lagging a couple of years ago in the tools, but they've really caught up in what's available. They're fairly rigid in their implementation of a lot of things, though. Linux, being Linux, is pretty freeform. We also looked at, did we have a preference of languages? And I just listed a few here. Python, Java, C#, C++. It didn't matter a lot to me as long as we could accomplish the goals. And then there's two big engines on the market, or libraries or methodologies, if you will, that you can, roads you can go down. One of them is called OpenCV. It's an open source one. And then one of them is TensorFlow. Both fairly good. Compare them side by side. See how they'd work in your project. When we got all through with that whole process, I like to show this slide right here. This is where we settled. We settled on we were going to build it on our Linux machines. We were going to build it inside of Python, and we were going to use OpenCV. And that was where we wound up. So from there, how are we going to go forward? What does the plan look like? So what we thought was going to happen is, remember, we were taking pictures before, so let's make it as simple as we possibly could. Let's simply add a blue cloth background, add a white note card in the top left of the blue cloth background, and then just put a little bit of spacing in between the potatoes, and then have an agreement that we're going to take pictures of 1 plant, 3 plants, 5, whatever the number of plants is that will fit on this blue cloth. So what we've done by doing this is we've eliminated the data entry, we've eliminated the scouts having to bring something back. We've told them, if you can do this one thing right, we can make it work. We tested this inside of bad light, good light, and everything else. You'll notice on this photo, there's places where you can see shadows. There's places where they're not spaced super well. The guy, and that would be me, that took the picture left his big dumb feet in it. And so there's a lot of problems with this photo. And also the cloth, I deliberately left it dirty just to show you all that when you process something like this, that is okay. So then we started running it through some detection algorithms, and boy, did we get an education in photo processing. So there's more steps than this. These are the ones that lend themselves to doing the best job. And the idea is you wanted to start with the picture in the upper left corner, and you wanted to wind up with the picture in the lower right corner. So if you started up in the upper left, ended in the lower right, then you had truly a black and white or a plated image, and you could go through that and tell it that find the potatoes. We've found holes, we've identified them as potatoes, and now we can guess their sizes. The reason we put the card in the upper left corner is it was a 4-inch by 6-inch index card, and that allowed us to correct for any parallax error or any adjustment error or any distance error. So we knew that was a known fact. We knew that was 4 inches by 6 inches on every single picture that was taken. And so from there, we could run the next set of algorithms. It was an edge detection algorithm that did kind of a square fitting and said, okay, draw boxes around the potatoes. This is a different run, by the way, if you caught that. Some interesting things about this photo is you can see this is 3.9 by 6 was the actual measurement. We told it, no, that's 4 by 6. And then it measured every potato on the screen. And now what we can do is we can have a log of every potato in that run. Fun fact about potatoes is generally the dimension, the width dimension, if you will, on most of these pictures, or the skinnier dimension, that matches the depth in most cases. So we were able to calculate 2 dimensions based on this, and then we could infer the 3rd dimension from the 2 that were calculated. Same blue cloth. This is a little earlier. So now with that, we've done our initial machine learning. Now we go back and we have millions of records of sample data, and we say these are russet Norcotas, and these russet Norcotas are this many weeks after tuber initiation. And so because of that, before, when we took the samples and actually weighed them, what did this size yield for potatoes? And we could infer what the weight was. Well, now we've captured length, width, height, or length and width. We've inferred height and we've inferred weight. Guess what? We now have been able to capture everything we wanted to capture. So the problem was, if you remember in the picture, we had to draw boxes around, and boxes have greater volume than cylinders, if you will. So we had to add a coefficient by variety to adjust for the weight shape. And when we added that coefficient by variety, one of the things that allowed us to do was say, okay, and this particular variety has more curves, so we're going to calculate the actual cubic size, but then we're going to reduce it by 15% because of this variety. And then this particular variety weighs this many milligrams per cubic millimeter, and we did it that way. And we let the computers calculate that for us using our old data. That allowed us to get yield forecasted, size distribution, and we can make intelligent management decisions. Technology delivered. We started this pilot in May. We started the actual testing of the product in May to test the potatoes and take the pictures, and on a limited basis. June 19th was a pretty good day. This was a slide I presented. I didn't change any of this. I presented this to the rest of the executive team on the 19th of June in 2019, and I said, hey, we compared we still ran the product to the Exeter, and we took actual weight, and we took the photos, and the result, our accuracy wasn't quite as good as actually measured, but it was better than any process we had in-house, which was fantastic. Our overall R-squared, or our deviation from what the actual was, the number was over 90, meaning it was very correlative. The largest error only seemed to be on the largest potatoes, and we weren't targeting those anyway. So we recommended large-scale field testing. I mean, we were very, very pleased with the results. Everything had gone extremely well. We call that a deploy and pop the champagne kind of moment along the way. Once we were done with that, reality set in. We scaled a little bit too soon. As the crop matured and things got larger, we found that accuracy began to drift, and it drifted actually by the end fairly significantly. We found that there were more irregularities in the shape. We found that the scouts that were taking the photos, as they got closer to the time of year they went back to school, they cared less about the spacing and getting some of it right. And so we had more potatoes that ran together, and that created some sizing anomalies. There was more dirt. You saw in the picture I showed you with my feet, there was some dirt, and we decided what an acceptable amount was. We were wound up with people that had a lot of dirt on the samples. People got lazy in the process, and we got lazy monitoring some of the results. And then the other thing we found with the agronomic team is we found some significant anomalies in their forecasting algorithms as well, which led to a lot of this. So a couple examples of finding fault. On this particular slide, you can see in the left slide, there is a little bit of dirt. If there were a lot more dirt than that, then the potatoes can run together. Also, if you look at the shadow on the first batch down on the two potatoes in the left column, you can see that the shadow almost makes them run together. That picture could, in sometimes, run into one potato, then that would be way too large. Second problem we had, if you look on the right at the picture, and you look at where I have the not good, you can see how that potato gets a little bit of an irregular shape. Here's a fun fact about potatoes. As they grow, when they start to get very large, or if they have sudden growth spurts, or if they bump into another potato, they will change direction like that, and you will get these kind of little issues and anomalies, and it will not give you the ability. So there's a whole bunch of area there that doesn't have a potato in it, and when we calculate the surface area or the cubic area of that potato, we would be wrong, and that would be definitely a problem. So that was one of the other lessons learned. So we shelved the project in 2020, or we didn't do anything in 2020. What we did in 2020 is we said, what do we have to do differently to make this successful? We actually went back and we took our entire data set and reran it in a Windows TensorFlow environment, found out that it was slightly faster, which was kind of a surprise to me, and the results were remarkably similar. So we didn't get any better or any worse results. We decided we were going to do a longer small scale trial. We were going to change our sizing algorithm a little bit. If I'm going to back up one slide, we talked about, if you look at the potato on the lower right side over there, we talked about breaking that up into pieces, and then how do we develop an algorithm to break the potato up to do a little more fitting, or do we actually work with a different AI or machine learning model set to train it to identify the actual potato as opposed to doing it the photo way. And we may go down that road. We're experimenting a little bit with that as well. We wanted to create a better feedback loop. We did a really good job of collecting the data, but we didn't go back and help our algorithms get better. And then we're going to move this from a research project to a product development project to hopefully take it a lot bigger as time goes by. So future plans. 2021, we want to restart it, meaning with next year's growing season, we're going to fire this project back up and bring it to a full conclusion, if you will. We want to integrate automated grading scores. So the second piece to this puzzle is not only what size is the potato, but does it have any defects? And by defects, does it have, and I won't bore all of you with what a potato defect is. Every potato has a certain number of defects, but they're blemishy things that make them not look so good. And they're generally caused by different things that happen in the growing season. And we feel we can accomplish that as well. We also feel that we're going to build an Android app. So instead of even having to submit it, we can hash the data, submit it to a server, and have it respond with what the yield and the distribution is in real time. And finally, possibly attach it to the harvester. Before I take questions, I just want to say a special thanks to my employer, the Wysocki family of companies. They brought me up here to work with a fun staff. We collaborated with Dr. A.J. Busson in the agronomy department and Dr. Mike Kopus. Had a lot of fun with those gentlemen. I've got an awesome technology staff. Any questions down the road, don't ever hesitate to contact me. My email is right there on the screen. And that gives us about 10 minutes for questions if anybody has any.
Hey Ward, I've got one. How
Okay.
big is the team that you work with there?
I have 4 people on my team that are dedicated to this, and then we have an integration group and a infrastructure support group.
Very cool. So no, I actually got the opportunity to tour a place like this, Heartland Farms,
Sure.
and saw their operation. I was blown away about like the amount of technology they use in all their operations.
I worked for an irrigation company in ag, and when a potato farm called me, I thought there's not that much technology in potatoes. And the thing that absolutely amazes me is probably the coolest technology in all of agriculture is occurring in the vegetable farming areas. So everything going on up here in central Wisconsin, if people want to get involved in this kind of technology, this is the area to find it, and these are the farms to find it on.
Yeah, I was kind of blown away about like the GPS systems they have when they're planting. You know, they're like accurate within like an inch.
Yep.
And you know the mappings they do for watering, so the targeting irrigation, like it was just amazing.
The beauty of it is you can target the mapping, you can target, I mean, and the goal now over the next 5 years will be to target the application of chemicals to that level. You know, why are we applying pesticides, if you will, to a whole field when you only have pests in one area? Why are we applying insecticides? Why are we, all of those things should be targeted, and we can reduce the number of chemicals in the environment. We can also reduce the costs to the farms as we go forward. It's really a fantastic trade-off we have.
Yeah.
AI is the next piece. I mean, I would encourage anybody looking at it to say, hey, jump in and learn about artificial intelligence, learn about machine learning. It really truly is where everything is going.
Was it hard to justify the cost of the project to the return on investment?
So that's a great question, and the answer to that, in a lot of cases, yes, it is. This project, the good news is if you look at the tools we used, we didn't have to buy a lot of new tools to do it, and our people were in the fields anyway. And it also probably helped that I'm on the executive committee that approves those things. So moving it to a project is going to be interesting, though. I mean, we're moving this to a full-blown, instead of an R&D project, it's going to be more of a commercial project, and there's going to be a higher bar we're going to have to meet.